only one component is operational at any given time without interference of another component. So again, just like that former picture you looked at, if you operated a selector valve that was in the middle of a chain of selector valves, we eventually run out of fluid to make an actuator downstream function. So you cut off flow to it. Okay. Also, one kind of thing to think about too is this is going to provide for slow actuator movement. You're building up pressure gradually as the fluid flow enters into the cavity of an actuator. It isn't, pressure isn't available instantaneously, not like other systems. So the flow from the pump eventually has to build in order to see confinement. So it's generally going to be kind of slow. Those open center selector valves had to have generally open center systems had to have a selector valve that kind of looked like this. I've copied this picture out of an old airframe book to show you the complexity of that open center selector valve. In a neutral or off position, this is what you would see in the selector valve. The fluid flow from the pump goes right through it and then circulates back to the reservoir. Inside of the selector valve, you've got a piston that's able to be shuttled one way or another, and you've got a handle outside of the selector valve that you can move one way or the other. When you move the handle one way, it drags the piston one way. When you move the piston or the handle the other direction, it shuttles the piston the other way. What that is doing is it's now diverting the flow from the pump to one side of the actuator or the other. So let's take a look in this case. What we've done is we've put the actuator or the handle in one particular position. It'll lock over center. So what happens is the spring on this thing in combination with an over center allows the piston to kind of be forced one particular way. So okay, we're now delivering fluid flow to one side of an actuator. So the fluid flow from the pump comes in through the inlet and goes out the port that's labeled as D. The fluid flow returning from the other side of that same actuator comes up port B, and then it exits out port C going back to the reservoir. Now, what makes the actuator or the selector valve go back to it on its own to the neutral position? It has to do with the surface areas that are exposed on either side of the piston and the selector valve. What happens is the pressure builds up to a point where the fluid then works on one side of the piston to push the actuator or push the piston back to its natural neutral position. And then flow then continues back from the pump to the reservoir. So once the actuator reaches full travel, it goes to the full end of its position, then it kind of goes back. There are some devices that are on these open center selector valves that provide for a little bit of adjustment. There's a little metering pin that they have on each side of the selector valve, and what that does is it kind of cushions the hydraulic fluid as it's going, as the piston is shuttling itself back to the off position. It's important that those little adjusting screws, those metering screws, not be fully opened or fully closed. If they're fully open, what it does is it provides an escape path for hydraulic fluid, and then the selector valve won't go back to its neutral position. On the other hand, if that adjustment screw is turned all the way in clockwise, as the piston is sliding itself back to the neutral position, the problem is the piston reaches incompressible liquid, and what do you suppose will happen to this selector valve? It's going to break. So again, the idea is that metering pin is kind of a cushioning device so that the fluid flow is forced to kind of gradually leave the valve as it slides back to the other position. So, but anyway, it's kind of an interesting device. If you want more information on it, I can drag out the book that shows you it, but this is what an open center selector valve had to kind of look like. There were other open center systems that diverted flow from the pump in order to be able to control an actuator, but most of the open center systems use something like this with a selector valve. These were pump discharge controls. Again, once the actuator reached full travel, these devices would allow the pump discharge to circulate back to the reservoir in order to prevent pressure from skyrocketing too high. But they're pump discharge controls. A more modern type of system might be a closed center hydraulic system. And let me show you that kind of a closed center hydraulic system. This is the idea behind a closed center system. Closed center systems means that you build up and hold hydraulic pressure and make it available for use as needed. This is just a generic picture of a closed center system. And again, when we're talking about the type of system closed center, it really refers to the selector valves that are used in the system. If you were to look at the selector valves, they do not have a hole in the center of the valve. The valve in this particular case is got a section on it that provides for no passage of hydraulic fluid. So it's called closed center. We can see kind of what happens in this particular case. The fluid from the reservoir passes to the engine-driven pump. The fluid flow then goes through a pressure regulator, sometimes called an unloading valve, and then the pressure is made available to the one side of the selector valves. Also, that hydraulic fluid enters into the cavity of the accumulator and pushes down a bladder or a diaphragm. So what we'll see happening is the pressure will begin to increase as the fluid is being confined in the circuit. So they call this closed center. Okay, well, we reach a point where there's just so much pressure that we really can't control it. So we've got a device called a unloading valve or pressure regulator. At a certain point of pressure, any additional flow from the pump is going to be channeled back to the reservoir, but we'll still hold whatever pressure we've had in the pressure manifold inside of the accumulator. The only time that pressure would drop would be if we operate a selector valve and then we divert the flow that's in this pressure manifold to make the actuator work. At some point, the regulator might say, or the unloading valve will say, introduce more fluid flow into the circuit to build up pressure. But generally speaking, once the pressure requirement has been met, the unloading valve provides a path for fluid flow to circulate from the pump back to the reservoir. So this is probably a more common hydraulic system that you'd see for an aircraft. What this does for you is it makes the actuators or the selector valves independent of each other. If you operate one selector valve, it doesn't matter if you operate another one. You're not dependent upon the fluid flow from one selector valve going to the next one because the selector valves are in parallel with each other. So it makes fluid flow immediately available to any actuator that you want to make work. So this is probably a more common type of hydraulic system for modern aircraft today. Do we still have to have a method of a backup for pressure control? Yes. This is a system relief valve. In its simplest form, it's nothing more than a massive ball held on a seat by a big spring. And the idea is if our unloading valve should fail, where the pressure starts skyrocketing too high, the relief valve will crack itself open, and a drop or two of hydraulic fluid will leave the relief valve and circulate back to the reservoir. So what that does is it controls system pressure as a backup. But it's certainly more complicated. You have to have a pressure regulator in this circuit, or at least a method of controlling pressure. What I'd like you to remember also is the selector valves are in parallel with each other, and they don't have an open center position generally. So when you stop the fluid flow and pressure starts to build, you're going to require a pressure regulator in order to control system pressure.
What's the TRV?
I haven't told you about those yet. When we get into the class, we'll talk about them, but basically they're thermal relief valves, TRVs. When the selector valves are positioned as they are now, there's fluid that's trapped inside of the cavity of the actuator. If the heat should cause, a heat buildup should occur, that heat buildup will cause the pressure inside of the cavities of that actuator to egregiously go out of control. So we have to find a method for controlling pressure. All they are miniaturized versions of relief valves, but they've got a very strong spring in them. And if the pressure should rise inside of the cavity, the thermal relief valves will provide for a brief instant opening. A drop of fluid will exit the cavity of the actuator, and the valve shuts itself off. So these are necessary because a lot of times the selector valves are positioned off. There's no way to vent trapped fluid that would expand as a result of thermal energy. So that's why you have to have TRVs in the circuit. Years ago, I had a problem with the S2F landing gear mock-up. There's a sequence valve that times the operation of the landing gear retraction with the doors. So the doors, the gear should come up and lock before the doors close. Well, when I put the landing gear handle to the up position, man, all of a sudden the doors are closing at the same time that the gear is coming up and they collide. And I thought for the longest time that the problem was the sequence valve in that circuit. But I had a sharp student that was in the class that figured it out for me. He was a boat technician for Mercury Marine. And he looked at the circuit and what he was able to figure out was one of the thermal relief valves that was in the pressure manifold had debris in it. How it got there, I don't know, but it was old hydraulic fluid that was really contaminated. And by having a thermal relief valve open, it exposed a path for both of the actuators to operate at the same time. So again, we cleaned the thermal relief valve out and replaced the fluid, and sure enough, that fixed the problem. But in any event, it's called a thermal relief valve. Let me give you also some of the advantages and disadvantages of closed center circuits. The advantages, no problem operating more than one actuator at a time. And again, you saw what happens with closed center hydraulics. Once you run out of juice in the circuit to make an actuator work, anything that's downstream of it sees no fluid. So that's it, make it work. Also, because you are holding pressure available all the time, the instant that you open a selector valve, the actuator will start to move. So it's not like a open center system where pressure has to build to a point and then the actuator moves. This thing is immediate. As soon as you expose the actuator to system pressure, it goes, it's moving. The disadvantages, pressure regulating and control devices are required. You have to have a pressure regulator in these circuits because you are building and holding pressure. And eventually you reach the material limit of what the components can stand. So, the components can break if you don't have it. System heat and component wear and tear. With this system, since you are holding and building pressure, you're going to have more wear and tear in comparison with an open center system. Another thing, the components are exposed to pressure at all times and are prone to leakage. So again, the relief valve that's in the circuit, exposed to pressure, anything that's in the pressure manifold sees pressure. The accumulator, all the components that are there. So again, this is kind of the problem with closed center. But again, life is not a perfect world, it's always a compromise, so that's why we do it. To kind of show you, let me go to this picture. The original Cessna citation, the 500 series Cessna, this one used a modified open center hydraulic system. But if you look and see what they did in the particular hydraulic circuit, they've got very few components that are in it. They had what did they use for components? They had retractable landing gear. They had a speed brake in the aircraft that was also hydraulically operated. And as an option, they had a thrust reverser. Those were the only components that they had in the original Cessna 500 citation that were hydraulic. The flight controls, they were all mechanical. Rudder, elevator, aileron, they're all mechanical, but those are the only things that were hydraulic. So what Cessna decided to do is they built upon the idea of using an open center circuit, but they've got a kind of a strange type of selector valve that allows you to operate the circuit okay. Well, okay, that's fine for the Cessna 500 series. And in this case, the only time you've built up 500 PSI is when you made that selector, you operated one of the components. By the way, too, I looked in the old Cessna manual. The nominal pressure that you had in the pressure manifold when nothing was operating was right around 60 PSI. It was very low. But if you look at the evolution of that aircraft, take a look at this. Let's take a look here. Here's a Cessna 600 series citation. Now we've got a lot of components that are hydraulically actuated. We've got a dependent brake system. We've got roll spoilers and aileron boost that uses hydraulics for aileron control. Speed brakes and ground spoilers. Environmental control unit fan. So they have a fan that for cooling. The landing gear retraction and extension system, thrust reversers, and nose wheel steering. It would be impossible to do something like this with an open center hydraulic system. You would have a series of valves that would all be in series with each other, and you could only operate one thing at a time. So again, we're not going to do that. we're gonna have to be able to operate multiple components at any given time. So we need to use a closed center system. What does that mean? It means that you're gonna have to have pressure regulation in the circuit. It means that, well, it's more complication than you normally have. One thing too that I wanna kind of point out, if you were to look at a schematic, without looking at too much other than what's in the schematic and trying to figure out if you're dealing with an open center system or a closed center system, look at the component here. You have an accumulator. I've told you already what the purpose of an accumulator is. What's the purpose of an accumulator? It builds and holds hydraulic pressure. Would you ever see one of those in an open center hydraulic system? Very good, the answer is no. If you're looking at any schematic and you happen to see in the schematic that there's an accumulator, it can't be an open center hydraulic system, because closed center hydraulic systems are designed to build and hold hydraulic pressure. Now, did I say that all closed center hydraulic systems have an accumulator? No. I said that if you see an accumulator in it, it cannot be an open center system. Not all closed center systems have an accumulator, but if I see one on the circuit, I know it's not open center. So, okay, so some things you might want to remember. By the way, too, we can get faster actuation of components by building more voltage as an electrical circuit. So by the time the next iteration of Cessna came around to the 600 series, it's a 3,000 PSI hydraulic system. So you're building and holding 3,000 PSI of hydraulic pressure. Just kind of a comparison of the two. So again, closed center system on the left, open center system on the right. All the selector valves in an open center system are in series with each other. In a closed center system, the selector valves are in parallel with each other. And remember what I told you, if you see an accumulator, a hydraulic accumulator in the circuit, it cannot be an open center type system. It has to be closed center, because the function of the accumulator is to build and hold hydraulic pressure, like the voltage in a battery. Okay. I'll let you read on your own some of the stuff in the Merrill Fluid Power book, but you can see for yourself. Accumulator, it's got to be what? Closed center. There's another one, closed center. Okay. Also too, here's a pressure regulator. You don't really know schematically what that kind of represents if you didn't have a legend down at the bottom. But obviously, if you've got a pressure regulator in the circuit, it's going to be closed center too. Something else as well. Look at the circuit. You've got two pumps that are in parallel with each other. This is common for a lot of aircraft. You might have multiple pumps that may or may not draw from the same reservoir. But you'll notice something too. They've got check valves that are after each of the pumps. That line over there tells me that it's a one-way valve. Those are check valves. The purpose of check valves that are installed with pumps, kind of interesting. It prevents reverse flow. Obviously, any check valve does. But let's say, for example, one of the shafts on those pumps becomes broken. The drive shaft becomes broken. If you didn't have that check valve installed on the line, let's say the shaft on this pump is broken, without the check valve here, the fluid flow, when this pump is operating, would attempt to do what to this pump? Run it backwards. It prevents motorizing in an operative pump. You may see an FAA test question involving check valves that are used at the discharge of pumps. One purpose of a check valve is, at a pump anyway, the discharge of a pump, it prevents motoring in an inoperative pump. So again, maybe the shaft on this pump has failed. By having a check valve installed here, it prevents the fluid flow from the pressure manifold going and trying to reverse the direction of the pump, which would be called motoring the pump. So again, it may be disabling our circuit. There's something that's kind of true too. Fluid takes the path of least resistance, like water. So rather than the fluid trying to anchor into the accumulator, the fluid flow would try to run backwards through a pump that's being motored, may even go back to the reservoir. So it prevents motoring in an operative pump. That's why we have it. Okay. I'll let you read this in your Merrill Fluid Power book, a little bit of info. Okay. Next, I want to talk a little bit about this. This is commonly done on a lot of aircraft. We've kind of cobbled together components to make things simplified. And in the case of this piece of equipment, the generic term would be a power pack. It's got generally all of the power components on it that are either mounted on a pallet or kind of segregated all together, so it's called a power pack. The term is kind of generic. It doesn't necessarily mean that they all have the same components, but what you might find in a power pack, you might find a reservoir, you might find a filter assembly, you might find an accumulator, you might find an electrically driven pump. And down here, again, they've got an electrically driven pump. They've got a electric pump attached to it. Over here, God only knows what they have in it. And here it looks like something that's been cobbled together after Kobe swap meet. But nevertheless, you see all the components that are kind of there. So it's electric pump, filter maybe, integral reservoir, maybe some pressure regulating devices that are all kind of attached together. So this would be an idea of what we would call a power pack. And again, it's a generic term. So all the components are in one segregated unit. This is kind of interesting too. Look at this picture. See the dotted box that's in that picture? I mean, you can't miss it, it's in red. But the dotted box points out to what we call a power pack for Beechcraft. In the Beechcraft aircraft, look what they have installed in their power pack. They've got a integral reservoir, they've got an electrically driven pump, they have a solenoid operated selector valve, they've got, let's see, what else do they have? They've got a filter in the circuit, they've got a system relief valve, all of that incorporated together. And also, they've got a pressure actuated switch that's in a part of the circuit too. The FAA will have a question for you as a test question. If you see a dotted box on a schematic, what does it indicate? What do you suppose it indicates? Power pack. I want you to remember that. Okay, all right. We look at other aircraft, for example. Let's take a look at what Piper does. On a lot of Piper single-engine aircraft, they use their version of what they call a power pack. It's an integral device that contains a reservoir, a reversible pump, electrically driven pump. It's got a valve that they call a shuttle valve inside of it, and also pressure regulating and limiting devices in the circuit. And a shuttle anyway. When we want to make the gear go up and down, a lot of single-engine aircraft, Pipers in particular, what we do is we run hydraulic fluid under pressure into one side of an actuator or another. So in the case of the Piper, what we do is if we want to retract the gear, we put the landing gear handle in the up position, and what that does is it runs the electric motor one particular way. What that does is it delivers flow from the discharge side of the pump in order to push hydraulic fluid into the actuators and raise the gear up. Pretty simple, okay? Eventually the gear comes up, and what they do is they use a limit switch in order to shut the electric motor off, or the electric motor that's driving the pump off. So okay, the pressure switch is here, the pressure goes up to a particular value, and again, it shuts off the electric motor that drives the pump. We want to put the gear to, you want to put the gear to the down position. You put the gear down, what it does is it drives the electric motor connected to the pump in the opposite direction of rotation, and it allows hydraulic fluid to enter into these cavities of the actuator, and it drives the gear down. Eventually, there are limit switches that tell the electric motor to shut itself off. So it's really a simple system. Something else that's kind of interesting too on Piper aircraft, with Pipers, they don't really have any locks to hold the gear in the up position. What they're doing is they're using hydraulic pressure that's retained on this side of the circuit in order to hold the gear up, which is kind of nice. If you were to lose hydraulic fluid, what would happen? The gear comes down, okay? So it's kind of a natural safety device. It'll come down under its own weight and generally lock in the down position. But again, it makes things nice and simple because, again, there's no really locks holding them in the up position. Also, too, if the gear should start to sag down when in flight, there's a pressure switch which would be activated, and that attempts to push the gear back up again. It engages the pump again so that it delivers flow to build pressure back up again. But anyway, in the landing gear class, Lyle will probably talk to you a little bit about this. Kind of interesting.
I'll also tell you that the bungee cords that assist that process.
Yeah, for everything to work right in the extension process for emergency extension, everything has to be in rig. You know, just because the hydraulic pressure gone does not necessarily mean that the gear's gonna lock correctly. I've got another story that I'll tell you later about a twin Comanche that we worked on later. But in any event, this is what they do on Pipers. Something you might want to remember with any type of electrically driven pump, many of the electric devices or electrically motor devices have a duty cycle. So for example, it says operating time 12 seconds maximum at 75 amps, and there's an auto reset after 12 seconds. The problem with a lot of things that are electrically moved is that there's heat that's built up, and you can burn out the electric motor if you operate it too soon, the accumulated heat. So sometimes they'll have a duty cycle that you have to abide by with many of these components, and if you jump the gun and operate it too many times or too quickly, you can burn up the electric motor. So you have to be kind of cognizant of that. But anyway, this is kind of the specs for what they use for a Piper power pack. Okay. All right, you're up, you're down. What does that dotted box mean again?
Power pack.
That's right. Okay. This is Cessna's idea of what they call a power pack. And again, for some Cessnas, what they've got is an integral reservoir and selector valves that they use for powering flaps and landing gear extension and retraction, and also emergency hand pump for extension of gear. Okay, next, a little bit about the specifics of things that are electrically driven, like pumps. Anytime that you've got an electric pump, we don't really have a true pressure regulator that's used in the circuit, but we still have to have something that's pressure sensing that turns the electric motor off. So what we use in a lot of times is a device called a pressure switch. The pressure switch is really a control for the electric motor that drives the pump. In many of the pressure switches, they have a device like a board-on tube. The board-on tube expands, and what it does is it separates the electrical contact that controls the electric motor that's driving the pump. So anytime you've got an electrically driven pump, don't be looking in the circuit for a pressure regulator. What I would be looking for is really a pressure switch. And the pressure switch, in this case, it's what we call a normally closed pressure switch. You can kind of see what happens. When we develop current flow through the electrical circuit and the switch contacts are closed, that's what's energizing the electric motor, and then the pump begins to turn. When the pressure builds up in the pressure manifold and starts to fill the accumulator, at some point the contacts on the pressure switch will open because the board-on tube starts to go erect, and then the contacts open. When that occurs, it stops the electric motor, which in turn shuts off the pump. If the pressure should drop, the board-on tube curls back up again. What happens to the contact points? They close. Then we deliver electrical power or electrical voltage to the electric motor, and then the pump starts back up again. So again, this would be an electrically driven pump, not an engine-driven pump. So that's what the control of that. These are also electrically driven pumps, but they're not really truly for hydraulic systems, but they have a somewhat of a hydraulic function. Does anybody kind of recognize that type of pump? It is an aircraft that originally started its life as a type of aircraft pump. Anybody?
Starter?
I'm sorry?
Starter? Starter?
Not a starter. Some of the hydromatic propellers that we had on older aircraft had to be feathered. You have to feather the propeller for emergency purposes. This was the pump, or actually even just changing pitch on a hydromatic propeller. So these are electrically powered pumps, but they provide for pitch change in the hydromatic propeller. They also allowed you to feather the propeller too. Well, they've been repurposed for another purpose. Does anybody have an idea what these things are now currently used for? That's what they're used for. So, you know, you see all of the lowriders that are out there. What they've done is they've cobbled together components and made the car do strange things. So again, this is how they do it. But inside of the trunk of those cars, usually they've got one of those electric pumps. It was in a former life was a pump from a hydromatic propeller, Hamilton standard, in order to be able to make it do that. This is what a pressure switch kind of looks like. At least one version of a pressure switch. It's got a board-on tube and switch contacts. There's a fluid port at the inlet of the pressure switch, and then you've got a cannon plug connector at the other end of it. When you build hydraulic pressure, it begins to make the boron tube go erect. It separates the electrical contacts and then cuts the electric voltage that's going to the electric motor. And then when the pressure drops off for any reason, eventually the tube curls itself back up, the contacts close, and then it starts the electric motor again. Electrically driven pump. Okay, so you can see some wiring that comes off of that thing. Next, I want to talk about kind of a different animal. I want to talk about maybe the reasons for pressurizing a reservoir. I think you realize with many simple hydraulic systems, you have atmospheric pressure that is pushing on the fluid. When you've got a simplified hydraulic circuit that kind of looks like this, you've got a reservoir, here's the pump, and it goes downstream to pressure regulator, and then ultimately goes to components. The reservoir itself is usually a vented reservoir. We've got maybe a vent opening with a tube coming down the side of it. And the idea is you've got atmospheric air pressure that's able to push directly on top of the fluid. And this works just well and fine at sea level. You've got the column height of liquid that is also aiding in delivering fluid flow to the pump, but you've primarily got also atmospheric air that's pushing on the fluid. But how about if we were talking about an aircraft that's got a reservoir for the hydraulic system and we're flying at altitude? You don't have the same amount of air pressure pushing on that liquid. You need some kind of assistive aid. So the primary purpose of pressurizing a reservoir, it prevents the power pump from cavitating. I'm going to send you a video concerning power pump or a cavitation of hydraulic fluid, but it's especially damaging to the pump. The problem is you're building up voids in the liquid that is really a vaporized form of the hydraulic fluid. As those vapor bubbles collapse, it imparts a tremendous force on the pump that's extremely damaging. So I'll send you a video that's very important. So by pushing on that fluid with an artificial method, what we can do is we can prevent cavitation from occurring. So it's a substitute for air pressure that you normally have at sea level. And the secondary purpose of a reservoir pressurization is, well, I can put the reservoir at any point relative to the pump. With a vented reservoir, where does that reservoir always have to be? It has to be above the pump because you're developing head pressure going to the inlet of the pump. You have to have it mounted above the level of the pump to some degree. With a pressurized reservoir, I can have the reservoir mounted at the same level of the pump, higher than the pump, or lower at the pump, because I will always have a push of hydraulic fluid that's available to the pump inlet. The methods of pressurizing a reservoir. Well, let's talk about the oldest method that I'm aware of. That would be maybe a Venturi T. We'll talk about these methods in just a little bit. But here's an example of a Venturi T just as a schematic. The idea is it takes ambient air into the throat of the Venturi and then allows that airflow to go into a line that ultimately terminates into the reservoir. It uses return system fluid to enter into the throat of the Venturi, and in doing so pulls ambient air into the throat and delivers that into the reservoir. Schematically, this is kind of what it looks like, but the actual components, I'm not able to find a picture of one used in an actual aircraft. But what it does is it develops air pressure that pushes on that liquid. Should a lot of hydraulic fluid flow try to return itself back to the reservoir, there's kind of a pathway through a valve that will allow some of the fluid to kind of bypass the Venturi T. But that's it. To prevent reverse flow of air, they've got a check valve that's mounted at the Venturi T. But this is probably the simplest method of pushing on the fluid to substitute for lack of air pressure that you might have. So Venturi T. Here's another picture of one from a book, kind of shows you the idea. And you realize with any type of Venturi, you're creating a drop in pressure by flow of hydraulic or flow of a liquid. So you have a high velocity created at the inlet of the Venturi that creates a lower pressure, and that would allow the air to enter into the throat of the Venturi. Here's one. I don't know what aircraft this came from, but I stole it from an old military manual. So they got a Venturi T installed in the line that goes into the reservoir. They also regulate that air pressure to about 8 psi. It doesn't have to be a great deal of pressure, but it certainly has to be enough to push on that fluid. So that's kind of the idea of a Venturi T.
Doesn't it tend to get air in the hydraulic fluid?
Well, yeah, the problem is, you know, the way that they have it illustrated, it looks like it dumps directly into the reservoir from the top. But in actuality, in many of the reservoirs, they've got like a separation plate or a foaming area that allows that air to somewhat separate before it gets to the inlet of the pump. So the answer is yeah. Okay. All right. There's another way of pressurizing reservoirs, and this is a device called an aspirator. And it uses also the Venturi technique, but what it does is it delivers flow from the engine-driven pump, and it routes it through the aspirator, drawing, in this case, cabin air in. So if we've got a pressurized reservoir, what we can do is we can steal that, but it kind of draws that airflow in through the aspirator in order to pressurize the reservoir. So another method of kind of getting air into it. Another type of a method of pressurization would be a device called a jet pump. And again, as you might expect, it's got a Venturi inside of it, and it's self-regulating to a degree. The idea is that we've got return system fluid that is going through the throat of the Venturi. It drags ambient airflow into the throat as well, and then delivers that into the reservoir. At some point, it's self-regulating because we've got a diaphragm that's attached to the jet pump. It pushes a piston or a rod up into the throat of the Venturi and blocks additional flow. So once you've got enough air pressure in the inside of the reservoir, it kind of cuts itself off. But okay, so that's called a jet pump. And another way that we could pressurize a reservoir is by pushing on it. We can have a piston on the inside of the reservoir that pushes directly on it, and may be assisted by air as well, maybe even a spring. But I've got a much better method of doing something like this. This is what you find in a lot of military aircraft for reservoir pressurization. They use a particular type of reservoir that they call a bootstrap reservoir. So the cavity of hydraulic fluid is over here. You can see what kind of is pushing on that fluid. They've got a piston inside of the reservoir. So as the piston is bearing against the fluid in this cavity is in fact pressurized. And this is going to the pump, okay? Actually, one line is going to the pump, the other line is a return line coming back from the system. So you've got fluid that's under pressure at all times. Well, the nice thing about this is with a bootstrap reservoir, the aircraft can go into unusual flight attitudes, and you don't ever have to worry about fluid falling away from the inlet of the pump. So if the aircraft performs a violent maneuver, goes into a roll, or maybe goes into maybe a steep climb, you don't have to worry about the fluid being available to the pump, because what you have is a piston that pushes directly on that liquid and makes it available to the pump. So okay, that's one big advantage. The way that this thing kind of works, when the fluid enters into, when you service the reservoir, you fill the reservoir up. Before you start the hydraulic system, there has to be something that initially pushes on that fluid. So before you start the hydraulic pump up, in order to make it work, you have to have a spring that kind of pushes on the piston. Oh, you may ask yourself, what was the actual force that's pushing or bearing against this piston? It's actually system pressure. What they do is they tap off of system pressure in the pressure manifold. It pushes on a smaller diameter piston. That force is translated to a larger piston by a rod that connects to it. So it cuts the amount of pressure that's available on the fluid. To kind of illustrate what's happening here, let's take a look. Let's say that we've got a 3,000 psi hydraulic system. Okay, let's say that the surface area of this thing is 1 square inch. How much force is imparted to that rod? 3,000 pounds. let's say the surface area of this thing is 100 square inches. How much is 3,000 divided by 100? 30. So the amount of pressure that the fluid sees going to the pump is about 30 psi. It's always a ratio of the sizes of the pistons that determines how much pressure is going to be applied to the inlet of the pump. So again, kind of an interesting thing. Oh, you may wonder too, what's this rod all about over here? Well, the rod is spring-loaded against the piston on this side of it. When the reservoir is completely filled, what that does is it provides for an indication of the quantity of fluid that's in that reservoir because the rod has been pushed out, it's buried against it. Additionally too, maybe the reservoir is over-serviced, you fill too much fluid in it. They've got another type of device inside of it that provides for a bleed of fluid so that it prevents too much fluid from actually entering into the reservoir. So the piston comes back far enough, it pushes the poppet over, and it allows some of the fluid to actually be bled out from one side of it. So they have that. It's an air bleed as well. You can pull on the handle. It'll allow some of the fluid that's on the side of it in order to be drained, or the air to be drained out of it. But it's called a bootstrap reservoir. Anytime that you see the term bootstrap, it means self-sustaining. So again, we're using system pressure on one side of the piston in order to be able to get some pressure on the other side of it for the fluid that's in the reservoir. So it's called a bootstrap type of reservoir. Does everybody kind of see what's going on with that thing? All right. All right. A floating piston. Piston floats back and forth. Okay. I didn't like this picture. This is what they show you in your airframe book, but I think this one's pretty damn good. The F-4 aircraft had a bootstrap reservoir in it. The small piston that's inside of this thing is really a system pressure. That in turn produces a force on a larger piston surface area that's inside of the reservoir, so the reservoir becomes pressurized. The L-1011 also used a bootstrap reservoir. It's got a small piston on one side of it and bigger piston on the other. And here's a cross-sectional view of it, of an L-1011 bootstrap reservoir. So again, on this side of the piston, they've got 3,000 psi. On this side of the piston, they've got about 85 psi. The ratio is 36:1. So again, we use system pressure itself in order to provide for a force against the fluid in the reservoir. Okay. Cessna Citation, bootstrap reservoir as well. This is kind of weird too. In some cases, the reservoir housing moves and that floating piston remains stationary, or vice versa. But in this case, they've got a tape reel that's attached to the piston. So as the piston slides back and forth, that provides an indication of fluid quantity that's in the reservoir. Okay. They also have some limit switches as well. There's a cam that's incorporated on the rod of the piston. And what it does is it operates an electrical switch, and it tells me when the reservoir quantity is low. So the piston position is really the indicator for fluid quantity. Cessna Citation as well. This is the 600 series. And again, they've got remote indication of fluid quantity, but they've also got a tape indication for fluid quantity in the reservoir. And again, you kind of have to look at the manual to see how it works, but that's it. Another bootstrap reservoir from an A4 aircraft. Got a floating piston inside of it. Pressurized reservoir. This one is not a bootstrap reservoir. This is more common to civil aircraft. With large commercial aircraft, we'll use air pressure directly on top of the fluid. What's the source of air pressure? It's usually regulated bleed air. So if we're talking about, like, for example, a 747 or an Airbus or other aircraft that are commercial aircraft, we usually push on the fluid directly, and that provides a source of pressure on the fluid. Military aircraft may have a separator or a baffle in the reservoir, but usually large civil aircraft do not. So, but that's how we do it. What I want you to remember also too, if we're using bleed air, which would be from the one section of compression from a gas turbine engine, we have to regulate that air pressure with an air pressure regulator. So you have to have an air pressure regulator in the circuit. Okay. This is what that air pressure regulator looks like. They've usually got bellows inside of them. The bellows expand and contract, and in order to regulate pressure. The reservoir, in this case, we're allowing bleed air to enter. The bleed air comes in, and ultimately what it does is it closes off the port when we reach a certain amount of pressure. And so the airflow is kind of going this way in order to fill the reservoir up with air. So the bellows expand, closes this port off. And then there has to be some method for controlling excess pressure. So there's another bellows that's inside of the regulator, and the poppet moves against a bellows in compression in order to provide a vented opening if the pressure becomes too great. And also we have to provide for vacuum relief inside of the reservoir. So sometimes they've got a little check valve that's mounted on the reservoir. This prevents the reservoir walls from imploding. So it allows air pressure to enter into the reservoir to prevent negative pressure from collapse. Okay. Circuit from your book that shows your reservoir pressurization. Again, usually bleed air. There is one negative thing that I can tell you about bootstrap reservoirs that makes them a little bit difficult to service. When you service a bootstrap reservoir, you have to have usually fluid under pressure that's allowed to enter into the reservoir. So that means servicing from a pressurized cart. So here's a picture of an A4 servicing cart. So it's not as simple as taking a cap off of the reservoir and filling it back up again. Because the piston is loaded against the fluid in the reservoir, you have to have something that overcomes the piston that's pushing on it. There might be a spring on one side of the piston, so you have to overcome the spring in order to add fluid back into the reservoir. Air pressurized reservoir, not too difficult to service. Many of them have a bleed feature that you can remove the air pressure from the reservoir before you open the cap up. And again, it prevents you from being covered with hydraulic fluid when it comes time to service the reservoir. Okay, air pressurized reservoir. This one again, got a fluid quantity gauge on the side of the thing. And notice it's got two fill marks on it. We'll talk about reservoirs next week. But it says full condition, the accumulator is discharged, and also full condition, the accumulator is charged. The accumulator holds a great quantity of hydraulic fluid, and sometimes you have to pay attention in servicing. You may think that the reservoir requires fluid because you see that the level has gone down, but what you don't realize is the fluid is just contained in another device. It's in the accumulator. So on many of the reservoirs, they provide a couple of full indication lines or marks. So one would be in the case if the accumulator is filled with fluid, and the other one would be the accumulator has been dumped. The fluid has been sent back to the reservoir. Air pressurized reservoir, this is from an E2 aircraft. It does have a piston inside of the reservoir, but air pressure is pushing on the piston to keep it in confinement. Anytime you're using air too, you have to be concerned with the quality of that air. In some cases, they've got a desiccant that's installed in the air line that goes into the reservoir pressurization system. So here's a desiccant, a chemical dryer, so that dries the air out as it enters into the reservoir. So sometimes they've got silica in them, and they're sometimes replaceable. And that's it. E2 aircraft. Oh, something kind of strange. With fluids, generally, when you apply heat energy to them, with most fluids, do they expand or do they contract? They expand. Well, on one particular aircraft, in this case would be the P3 aircraft, what they did was they allowed the theory of fluid expansion to provide for reservoir pressurization. As the fluid becomes hot in operation of hydraulic components, it allows the fluid inside of the reservoir to expand. What that does is it decreases the volume of space above the fluid in the reservoir and provides for the push of fluid on that fluid. So the P3 aircraft did this. It's a strange Lockheed type of deal. The P3 aircraft was the only aircraft that I know that did this, but maybe the 188 Lockheed Electric did it. I don't know. But in any event, it's kind of a strange way of pressurizing the reservoir, and it relies upon the heat of the fluid to cause the liquid to expand, and then it allows the cavity of air above the reservoir to become pressurized, and that's what's pushing on the fluid.
Basically, they just seal off the vent.
Yeah, so that's it. It's kind of a strange method. I don't know of any other aircraft that did that.
If it works,
It works. Oh, there is one other way of kind of cheating to prevent prevent cavitation. Let's kind of jump ahead a little bit and maybe take a look at let's see this. The C-130, the Lockheed C-130. It is, the reservoir is really a non-pressure. There's several reservoirs in the aircraft. They have a booster system, and they also have a utility system. The reservoirs are pressurized. However, they have something between the reservoir and the engine-driven pump. What do you suppose they have?
boost.
They've got a booster pump. They've got an electric pump. So on the C-130, the way that they prevent cavitation is by having a booster pump that's electrically powered. And what that does is it pre-pushes on the fluid before it gets to the engine-driven pumps. So again, this is their solution to prevent cavitation of the pump. So that's how they did it. On some of the Boeing aircraft as well, in addition to having an air pressurized reservoir from bleed air, they may also have a pump that has got multiple stages on it. The initial stage of fluid goes through an impeller that puts an initial push on the fluid, and then after that, the fluid, it goes into the pump proper, and then from that point on, the fluid is now, it prevents it from cavitating. So that's how they do it in some Boeing aircraft too. Okay, so that's what I can give you on reservoirs, or at least on reservoir pressurizations. I'll send you a video this weekend. Take the time to watch it. It's really old school. I think it was done probably in the late 1950s or early 60s, but there's some very interesting things, and I want you to understand the concept of cavitation. So take a look, spend the time watching the video. It's actually pretty good. Okay. All right, so that's what I can give you for tonight. Any questions in particular about reservoir pressurization? So different methods of pressurization, you might have what? You might have a Venturi T, you might have an aspirator, you might have a jet pump, you might have bleed air that's regulated bleed air. You might have a method of pushing on the fluid with a floating piston. That's called what type of reservoir? Bootstrap. Okay. You see a dotted box in a schematic around the components that indicates what? Power pack. Let's see, what else? You know that pumps do not create pressure. What do they create? Okay. And we create pressure by what means? Restriction or confinement. Very good. All right. I guess I've done my job. I think I have. Okay, I'll see you out in the shop. Thank you.